So we have said that we will measure the time efficiency of algorithms only up to an order of magnitude. So we will express the running time as a function t of n of the input size n, but we will ignore constants. So we will only say that t of n is proportional to n square or n log n or 2 to the n or something. So now the next step is to have an effective way of comparing these running times across algorithms. If I know the order of magnitude of one algorithm and the order of magnitude of another algorithm, how do I compare them? So the notation we need, or the concept we need, is that of an upper bound, which is given by the notation big O. So we say that a function g of n is an upper bound for another function t of n if beyond some point g of n dominates t of n. Now remember that g of n is going to be now a function which is an order of magnitude. So we have thrown away all the constant factors which may play a role in g of n. So we allow ourselves this constant. So we say that it's not g of n alone which dominates t of n, but g of n times some constant. So there is a fixed constant c, okay? And beyond some limit, so there is an initial portion where we don't care, okay? But beyond this limit, we have that t of n always lies below c times g of n. In this case, c times g of n is an upper bound for t of n, and we say that t of n is big O of g of n. So let's look at an example. So supposing we have this function t of n is 100n plus 5, then we claim that it is big O of n square. Now remember that n is supposed to be the input size. Okay? So the input size to a problem is always going to be at least 1. There's no problem that needs to be solved if your input is 0, and certainly we cannot have negative input. So we are always having in mind the situation that n is bigger than or equal to 1. So if we now start with our function 100n plus 5, then if we choose n to be bigger than 5, then n will be bigger than this value. So we can say 100n plus 5 is smaller than or equal to 100n plus n. And now we can collapse this as 101. Right? So 100n plus 5 is smaller than 101n provided n is bigger than or equal to 5. Now since n is at least 1, n square is bigger than n. So 101 times n is going to be smaller than 101 times n square. So by choosing n0 to be 5 and c to be 101, we have established that n square is an upper bound for 100n plus 5. So 100n plus 5 is big O of n square. Now we can do this using a slightly different calculation. So we can say that 100n plus 5 is smaller than 100n plus 5n for n bigger than 1, because n is at least 1. So 5 times n is going to be at least 5. So now if we collapse this, we get 105n. Now by the same logic, 105n is smaller than 105n square whenever n is bigger than 1. And so we have a new way of establishing the same fact, where we have chosen n0 equal to 1 and c equal to 105. Right? So n0 and c are not unique. Right? Depending on how we do the calculation, we might find different n0 and different c, but it doesn't matter how we choose them, so long as we can establish the fact that beyond a certain n0, there is a uniform constant c such that c times g of n dominates t of n. Now notice that the same calculation can give us a tighter upper bound. This is kind of a loose upper bound. We would expect that 100n is smaller than n square, but we can also say that this is big O of n. Why is that? Because if we just stop the calculation at this point, we do not come to this stage at all. We have established that 100n plus 5 is less than or equal to 101n. Therefore, for the same values, n0 equal to 5 and c equal to 101, this also tells us that 100n plus 5 is big O of n. Likewise, at this point, if we just ignore this step, then we say that 100n plus 5 is smaller than 105n. So for n0 equal to 1 and c equal to 105, we have established this one. Let's look at another example. Supposing we look at 100n square plus 20n plus 5. Now again, assuming that n is bigger than 1, we know that we can multiply by n and it will not get any smaller. So 20n will be dominated by 20n square, right? And 5 will be dominated by 5 times n, 5n square. So I now have 100n square plus 20n square plus 5n square is bigger than my original function, 100n square plus 20n plus 5. So I combine these, I get 125n square. And now all I have assumed is that n is bigger than or equal to 1. So for n0 equal to 1 and c equal to 125, we have that n square dominates 100n square plus 20n plus 1. So you can easily see that in general, if I have a n square plus bn plus c, right? This is going to be dominated by a plus b plus c times n square. Okay, so this is going to be less than this for all n greater than or equal to 1. Right? So we can, generally speaking, take a function like this and ignore the lower terms because they are dominated by the higher term and just focus on the value with the highest exponent. So in this case, in this whole thing, n square is the biggest term, therefore this whole thing is going to be big O of n square. So this is a very typical shortcut that we can take. We can just take an expression, ignore the coefficients, pick the largest exponent and choose that to be the big O. Now we can also show that things are not big O. So for instance, it's intuitively clear that n cubed is bigger than n square. Now how do we formally show that n cubed is not big O of n square? Well, supposing it was, then there exists some n0 such that for all n bigger than or equal to n0, n cubed must be smaller than or equal to c times n square. Right? If this were big O of n square, this is what we must have. Now, supposing we choose n is equal to c, then we have on the left hand side c cubed. On the right hand side we have c cubed, and certainly we have the c cubed less than or equal to c cubed. But if I go to c plus 1, I will have c plus 1 whole cube. On this side I'll have c times c plus 1 whole square. And now the problem is that this is bigger because c plus 1 whole cube is bigger than c times c plus 1 whole square. And therefore, no matter what c we choose, if we go to n equal to c, we will find that the inequality that we want gets flipped around. Therefore, there is no c that we can choose to make n cubed smaller than c n square beyond a certain point, and therefore this is not big O. So our intuitive idea that n cubed grows faster than n square can be formally proved using this definition. Now here is a useful fact about big O. If I have a function f1 which is big O of g1 and another function f2 which is big O of g2, then f1 plus f2 is actually dominated by the max of g1 and g2. You might think it is g1 plus g2. This is the obvious thing that comes to mind looking at this, that f1 plus f2 is smaller than g1 plus g2, but actually it is max. Okay? How do we prove this? Well, it's not very difficult. By definition, if f1 is big O of g1, there exists some n1 such that beyond n1, f1 is dominated by c1 of g1, c1 times g1. Similarly, if f2 is big O of g2, there is an n2 such that beyond n2, f2 is dominated by c2 times g2. Right? So now what we can do is we can choose n3 to be the maximum of n1 and n2, and we can choose c3 to be the maximum of c1 and c2. So now let's see what happens beyond n3. Beyond n3, both these inequalities are effective. So we have f1 plus f2 will be less than c1 times g1 plus c2 times g2. Right? Because this is beyond both n1 and n2, so both f1 is less than c1 g1 holds and f2 is less than c2 g2 holds. So I can add the two, and this is the first obvious thing that we said, is it g1 plus g2. But now we can be a little cleverer. We can say that, okay, we have c3, so c1 is smaller than c3 because this is the maximum, c2 is smaller than c3, so I can combine these and say that this is less than c3 g1 plus c3 g2. Now having combined these, I can of course push them together and say this is less than c3 times g1 plus g2. But g1 plus g2, if I take the maximum of those, then 2 times the maximum will be bigger than that. So I will get that this is less than c3 times 2 times the maximum of g1 and g2. Right? Now I can take this 2 out and say that therefore this is less than or equal to 2c3 times max of g1 g2. Right? So now if I take this as my n0 and this as my c, then I have established that for every n bigger than n0, namely max of n1 and n2, there is a constant which is 2 times the max of c1, c2 such that f1 plus f2 is dominated by c times max of g1, g2. Now why is this mathematical fact useful to us? Right? So very often when we are analyzing an algorithm, it will have different phases. It will do something in one part, then it will continue to do some other thing and so on. So we could have 2 phases phase A which takes time big O of GA, and phase B which takes time big O of GB. So now what is a good upper bound for the overall running time of the algorithm? So the instinctive thing would be to say GA plus GB. But what this result tells us is that it's not GA plus GB that is useful for the upper bound, but the maximum of GA and GB. Right? In other words, when we are analyzing an algorithm, it is enough to look at the bottlenecks. It goes through many steps. Look at the steps which take the maximum amount of time. Focus on those, and that will determine the overall running time of the algorithm. Right? So when we look at a function, an algorithm which has a loop, we typically look at the loop. How long does the loop take? We ignore maybe the initialization that takes place before the loop or some print statement that takes place after the loop, because that doesn't contribute as much to the complexity as the loop itself. Right? So when we have multiple phases, it is the most inefficient phase which dominates the overall behavior, and this is formalized by the result we just proved. Now there is a symmetric notion to an upper bound, namely a lower bound. Right? So just like we said that T of n is always lying below C times G of n, we might say that T of n always lies above C times G of n. And this is described using this notation omega. So this is just a symmetric definition. It just says that T of n is omega of G of n if for every n beyond n0, T of n lies above C times G of n for some fixed constant C. So here we have the same thing. We have an initial thing that we are not interested in, because at this point nothing can be said. But beyond this n0, we have that T of n lies above. Okay, so T of n is always above C times G of n. So we earlier saw that n cubed is not big O of n square, but intuitively n cubed should be lying above n square. And this is certainly the case because n cubed is greater than equal to n square for every n bigger than equal to 1. Right? So at n equal to 1, both are 1, but n equal to 2, this will be 8, this will be 4, and so on. So given n0 equal to 0 or n0 equal to 1 and c equal to 1, we can establish this pattern. Now, of course, when we are establishing an upper bound, we are usually talking about the algorithm we have. We are saying this algorithm has an upper bound of so much, and therefore I can definitely solve the problem within this much time. Now, when we are talking about lower bounds, it is not that useful to talk about a specific algorithm. It's not so useful to say that this algorithm takes at least so much time. What we would like to say is something like this problem takes at least so much time. No matter how you write the algorithm, it's going to take at least so much time. So typically what we would like to do to make a useful lower bound statement is to say that a problem takes a certain amount of time no matter how you try to solve it. So the problem has a lower bound rather than an algorithm has a lower bound. Now, as you might imagine, this is a fairly complex thing to say because what you have to be able to show is that no matter how clever you are, no matter how you design an algorithm, you cannot do better than a certain thing. This is much harder than saying I have a specific way of doing it and I'm analyzing how to do that. So establishing lower bounds is often very tricky. One of the areas where lower bounds have been established is sorting. Okay? So it can be shown that if you are relying on comparing values to sort them, then you must do at least n log n comparisons no matter how you actually do the sorting. So no matter how clever your sorting algorithm, it cannot be faster than n log n in terms of comparing elements to each other. But this is hard to do, remember, because you have to really show this independent of the algorithm. Now, we could have a nice situation where we have matching upper and lower bounds. So we say that T is theta of G of n if it is both big O of G of n and omega of G of n. In other words, with suitable constants, T of n can be dominated by G of n and it also lies above G of n for two different constants, of course. Okay? So what this really means that T of n and G of n are basically of the same order of magnitude. Okay? They are essentially the same function. Okay? And therefore, you have reached a kind of optimum value. So as an example, we can say, for instance, that n into n minus 1 by 2 is theta of n squared. In order to prove something like this, we have to show that there is an upper bound, that is, we can find a constant such that c times n squared dominates this, and a lower bound. There's another constant that says c times n squared is below this. So for the upper bound, we just expand out n into n minus 1 by 2, so we get n squared by 2 from the first term and n minus n by 2. Now, since it is an upper bound, n squared by 2 minus n by 2, if I ignore the n by 2, this is going to be less than n squared by 2. And therefore now I have an upper bound saying that with a constant half, this is dominated by n square for n bigger than 0. On the other hand, if I want to do a lower bound, okay, then I will say the same thing. I will expand out n into n minus 1 by 2. I will get the same expansion. And now I will want a lower bound, right? So now what I will do is I will make this even smaller. Okay, so I will say that I subtract not n by 2 but n by 2 times n by 2. Right? I subtract more. So this will be bigger than this because I'm subtracting more. So n squared by 2 minus n by 2 will be bigger than n squared by 2 minus n squared n by 2 into n by 2. But this is again n squared by 2. Sorry, this is n squared by 4. Right? So this is n squared by 4. So I have n squared by 2 minus n squared by 4. So this simplifies to n squared by 4. So in other words, I've shown that n into n minus 1 by 2 is bigger than or equal to n squared by 4. But now, in order to justify this, okay, to justify that n by 2 is this is increasing, n must be at least 2. Because if n is smaller than 2, this is a fraction, and so I'm actually reducing a small. So here I have a different n. I have n greater than or equal to 2. So I have established a lower bound which says that for n bigger than or equal to 2, n into n minus 1 by 2 is above 1/4 of n square. So therefore now if we choose our constant to be 2, for all values bigger than 2, I have that n into n minus 1 by 2 is less than half of n square, and n into n minus 2 is bigger than 1/4 of n square. So I have found this matching upper and lower bound, which shows that n into n minus 1 by 2 is actually theta of n square. So to summarize, when we use big O, we have discovered an upper bound. So if we say f of n is big O of g of n, it means that g of n dominates f of n, so f of n is no bigger than g of n. And this is useful to describe the limit of the worst case running time. So we can say the worst case running time is upper bounded by g of n. On the other hand, if we use omega, we are saying that f of n is at least g of n. G of n is a lower bound for f of n. As we described, this is more useful for problems as a whole, sorting as a general problem, rather than for individual algorithms, because it tells us that no matter how you do something, you will have to spend at least that much time, but this is hard to establish. And if you have a situation where a lower bound has been established for a problem, and you find an algorithm which achieves the same bound as an upper bound, then you have found in some sense the best possible algorithm, because you can't do any better than g of n because we have a lower bound of g of n, and you have achieved g of n because you have shown your algorithm is big O of g of n. So theta is a way of demonstrating that you have found an algorithm which is asymptotically as efficient as possible.